Hi guys, welcome back to my channel. So now before I move on to set theory and partitions, filtration and everything else, I just want to start and introduce the idea of a fair game. All right, we won't use this immediately, but we will use this later when we are trying to price our first option using the binomial model. All right. Now, whenever I say price something or price an option and I don't mention what it is, I always mean that it's the vanilla option, all right? Throughout this entire series, we are only going to deal with the vanilla option and nothing else. So I just want to introduce what fair games are, all right? And with that, I'll introduce this with an example. So consider a betting game where we have two players. Let's say that player one is John and player 2 is Mark. Okay. And if the game is favorable to John, then his expected winnings will be at least as much as Mark. Okay. If the game is favorable to John, game is favorable to John, then his expected winnings, the expected winning of John is greater than equal to the expected winning of Mark. All right. Now, when I say expected winnings, I mean the net winnings, which means that to calculate it, we subtract any losses and treat the loss as a winning of a negative magnitude. All right. Now, I can apply the same logic and I can say that if the game is favorable to Mark, then the expected winning of Mark is greater than or equal to the expected winning of John, right? I'm applying the same logic here. Now, with this same logic, I can say that if the game is favorable to both the players, or if the game is fair, then the expected winning of Mark is equal to the expected winning of John, right? So if the game is fair to both of them, fair to both, then I can say that the expected winning of Mark is equal to the expected winning of John, right? No one has the upper hand here. So this basically means that what I can say with this, what I can say is that if the total bets placed by both Mark and John are, let's say, SJ and SM, right? If this is the input in the betting game that they're playing, the output too will be SJ plus SM, right? I mean, yeah, you can't add more money anyway. If the input is SJ plus SM, then the output is SJ plus SM as well. But if the game is fair to both Mark and John, their expected winnings are zero. That means this basically means that the total output SJ plus SM is a zero-sum game. All right, and I can write it as expected winning of Mark plus expected winning of John is equal to input minus output, which will be zero. Okay, so now a zero-sum game, which is this one, a zero-sum game is a fair game if and only if the expected winnings of each player is zero. All right. Now let's look at this with an example. Let's drive home this theory with an example. All right. I'll take two examples, in fact. Example one is, let's say that they're playing a betting game. All right. And if head turns up, John wins. And if tail turns up, Mark wins. All right. And they both bet $5 each. Okay, $5 each. If head turns up, then John gets $5 back. So his total earnings is $10, which is $5 of the initial investment and $5 that he won from Mark. Likewise, if Mark wins, then he gets back $10, which is $5 of the initial investment and then $5 that he got from John. Right? So I can write the expected winning of John. So also this is a coin tossing betting game, right? So I'm assuming that the coin is fair and it's not biased. So there's an equal probability of heads coming up and there's an equal probability of tails coming up. So over the very long run, like if you take 1,000, 10,000, 100,000 trials, all right, the number of heads is going to be equal to the number of tails, right? So expected winning of John is equal to let's say in total there are going to be 1,000 coin courses. So it's going to be 500. He's going to win 500 times. He's going to get ahead in a very ideal scenario 500 times, and his expected winning is going to be 100 into 10 minus 5 plus 500 into 0 minus 5. Sorry, 0. Yeah, 0 minus 5. And 500 is the number of times he wins over here, and this is the total number, the total amount that he wins. And this here is the number of times that he loses because he gets a tail, and this is the total amount that he loses. All right, and this turns out to be 0. Similarly, for the expected winning of Mark is 500 into 500 into 10 minus 5. This is the number of tails coming up plus 500 into 0 minus 5. Again, this is equal to 0. And now, because the expected winning of John is equal to the expected winning of Mark, we can say that this is a fair game. So I can write a general formula for the expected winning of a person. Let's say it's John. I can write this as the total number of outcomes, okay, into the total number of the total outcomes. So I can take the number of games, which in this case is 500, into the probability of an outcome, the probability of an outcome. All right. So in this case, the probability is half in each type. So if there's a half, the probability of a head turning up is half, and the probability of a tail turning up is half. And the last one is the winnings of an outcome. All right. Winnings of an outcome. So applying the same formula here, I have the number of games, which is 500. The probability of the outcome, the probability of a head turning up is half. I haven't written it here because I just thought it was obvious, because I said that's a biased, it's an unbiased coin. And the winnings of an outcome is 10 minus 5, which is 5, right? Plus, again, the total outcomes, plus the number of games, which is 500, plus the probability of an outcome, which is half for the tail coming up, and the winnings of an outcome. He's going to lose if he gets a tail. So the winning is of negative magnitude, which is minus 5. So this is my general formula that I can write for the expected winnings of a person, right? Now let's take another example where the probability is not similar. Example 2. So in example 1, we said that the probability of the head and tail turning up is equal because it's an unbiased coin. But what if the coin is biased, all right? And also, what if the amount of money that's bet by John and Mark is different? So let's say John bets $3 and Mark bets $7, right? And there's an 80% probability, which is 8 by 10, that a head turns up on the coin. Okay, and there's a 2 by 10 probability that a tail turns up on the coin. So this is basically just 4 by 5, and this is 1 by 5, right? So now what will be the expected winning of John? So applying the same formula here, I can write the number of games, which is again 500 into the probability of the outcome. The probability of a head turning up is 4 by 5 into the winnings of an outcome. The winnings here will be 10 minus 3 because he's going to get back $10 if he wins, including the investment that he gave, the initial investment, which is 3, plus 500 if a tail turns up into 1 by 5. This is the expected winning of John into 0 minus 3. Alright, so if you calculate this, you will get 5. Alright, so the expected winning of John is equal to 5. Now if I apply the same idea to Mark, expected winning of Mark. So in his case, if a head turns up, the probability of a head turning up is again 4 by 5, but he's gonna lose all of his money if the head turns up, so it's going to be 0 minus 7. And the probability of a tail turning up is 1 by 5, and he's going to win if that happens. So this is his winning probability. Alright, and if we add this, we get 7. I think we get minus 5. Yeah, we get minus 5. So the expected winning of Mark is equal to minus 5. Now, it's easy to see that this is not a fair game because the expected winning of John is greater than the expected winning of Mark, right? So it's easy to see that this is not a fair game. So there are multiple ways of making this a fair game. You can work your way back to see how this becomes a fair game, all right? So if I want to make the game fair to both John and Mark, I want to make sure that let's say that's a zero-sum game, all right, and the probability that this is for John, the probability that he gets 10 there's this probability p that he gets 10 minus x, and there's this probability 1 minus p that he gets minus x. So p is the probability that he wins, all right. This is the case for John, and 1 minus p is the probability that he loses this. So I can choose, if I take one parameter as constant, I can decide the other, all right. So let me take the bets placed by John and Mark as constant. So I'm assuming that again, John places $3 and Mark places $7, okay, John and Mark. So I can write this as P into 10 minus 3 plus, plus 1 minus P into minus 3 is equal to P into minus 7 plus 1 minus P into 3. Alright, this is for Mark, because if the probability turns up, he's going to lose $7 to John. And if the probability of, and if a tail turns up, he's going to win $3 from John. Alright, so this is actually 10 minus 7. Yeah, this is actually 10 minus 7. I just written 3 over here. So if we calculate this, we get P to be 3 by 10. Okay, so P comes up to be 3 by 10. So we can backtrack away and we can see that if we want the game to be favorable or fair to both John and Mark, the probability of a head turning up should be 3, and the probability of a tail turning up should be 3 by 10, and the probability of a head turning up should be 7 by 10. So I'm going to stop this video here. I just want to drive home the point of what a fair game is. We won't use it immediately. I'm going to go on to set theory after this, but we will come back to the same concept when we are pricing our option using the binomial model, the first pricing of the option. All right. So I'll stop the video here and I'll see you in the next video. Thanks.